Good day, everyone. My name is Salah Ismail. You're welcome to another series of our discussion in chemistry. Today, we shall be discussing one of the very most fundamental and interesting topics in chemistry, which is often evaluated in every examinations, in UTME examinations, in WAEC examination, NECO, and others. So, our topic of discussion is centered upon one of the fundamental conceptions discussed mostly on the periodic table. So, today we shall be examining the transition metals. So the transition metals is one of the very much important aspect of the metals in the periodic table. So we shall be evaluating the basic conceptions of transition metals. What are the features and the properties of some of these transition metals? How do we identify them? And how do we make the extractions? And several other things related to this topic. So I want you to relax and enjoy today's session. As you can see here, we have a little description of the transition metals, showing a number of elements extracted from the periodic table. We have the scandium, we have titanium, we have vanadium, we have chromium, and others. So these are actually elements showing the transition metals, and they have their own basic and special features. So at the end of today's discussion, well, these objectives are very enormous. So the series of this discussion is going to be divided into about 3 series. So our objective for today is mainly going to be on identification of elements here, most importantly identification of the transition metals. First, second, and the third role series, we are also going to look at how do we write the electronic configuration of the first transition metals, and also we shall be enumerating the general properties of these transition metals, so vis-a-vis the physical and the chemical properties. And lastly, we shall be identifying compounds of transition metals. So others are actually conceptions that we shall be discussing in the next series. So without wasting much of our time, as you can see here on the screen, what are transition metals? Okay, so transition metals are basically known as a d block element with unique chemical properties, in which there is a partially filled d orbitals. So summarily, when we are discussing transition metal, we are actually referring to special types of elements that possess electrons in their d orbitals. So elements generally are made up of a number of orbitals, but the special form of orbitals that have electrons filled in to their d orbitals, we call these type of elements, we call them d block elements. We call them transition elements. Now, transition elements can in other way be defined as elements with partially filled d electrons. Element with partially filled d electrons. So meaning their d orbitals or their d block orbitals have electrons that are partially filled. So the maximum number of electrons in the d orbital is actually about 10, right? So a situation whereby a particular element has electrons filled into this orbital, but the orbital is not up to 10 electrons. So we can also see here that these transition metals in question are located very much between group 2 and group 3 of the periodic table. So we can see the locations of these transition elements are between group 2A and group 3A of the periodic table, down around period 4. So this is exactly where we find them in the periodic table. So if you look at this periodic table, for example, so the location of the transition metal is around, this is group 1, we have the element in group 1 here, this is group 2 here, and then we have the group 3A here. So all these are group 1A, group 2A, then you have the group 3A here. So in between them you have the B groups. So within the B group sections, you have between group 2A and group 3A, you have the transition metals found. And this is located around period 4. This is after calcium. So we can see them located here. So this is exactly where we find these transition metals. And they are basically made up of 3 different rows. We have row 1, row 2, and row 3 transition metals. So these are the 3 major rows upon which these transition metals are located. So in addition to that, the transition metals, just like we said, have partially filled d electrons. So we are going to examine what makes them different. Why do we call them transition metals from the basic conception of our definition, and how we can identify those that are not true transition metals. So from the series, we said that the transition metals are basically divided into 3 major series. So we have the first series, the second series, and the third series. So our major focus for this discussion is going to be on the first series. Now we have scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. So as a student of science, as a student of chemistry, it's quite important that you know how to recall these transition metals offhand from 21 at least to 30. So I used to use an acronym for every student to recall this. So the simple acronym sometimes that could be used so that you can recall this could be Science Thesis Verdict Coil Masters in Congo Need Copper Zinc. So let me put it down here. Science Thesis Verdict Coil Masters need copper zinc. So with this, if you are able to recall this acronym, then it will be very easy for you to always remember the first rule of the transition metals. So Science Thesis Verdict Coil Masters in Congo Need Copper Zinc. The first one stands for scandium, SC. This stands for titanium, Ti. This stands for vanadium, V. This stands for chromium, Cr. This stands for manganese, Mn. This stands for iron, Fe. This stands for cobalt, Co. This stands for nickel, Ni. This stands for copper, Cu. And this stands for zinc, Zn. So here we have the series of the transition metal from 21 to 30. So this is scandium 21, titanium 22, vanadium 23, right, chromium 24, right, manganese 25, iron 26, cobalt 27, nickel 28, copper 29, and zinc 30. So here we have these transition metals and their atomic numbers. It's quite important for us to remember this. So with these transition metals, so it's going to be easier for us to be able to write the electronic configuration and to detect what exactly is the number of electrons in the electronic configuration. So let's begin with the first transition metals. So the first transition metals in question is actually scandium, Sc. So scandium with atomic number of 21. To write electronic configuration, I think it's important for us to do a little review on using Havard principle to write electronic configuration. So let me just take a quick review on that so that we can actually recall how we write electronic configuration using Havard principle. Now, to follow the principle, we always begin with 1s, 1s, 2s, 3s, 4s, 5s, 6s, and so on and so forth. So we have 2p here, 3p, 4p, 5p, 6p, and so on and so forth. Then you have the 3D, 4D, 5D, 6D, and so on and so forth. Then you have 4F, 5F, 6F. So with this, then you can begin to reshape and restructure this way, this way, this way. You just have to follow the way it is aligned, this way, and so on and so forth. So the very first orbital here is the 1s orbital, so that's 1s. The next one is the 2s, following that order. The next one is the 2p, right? The next one is 3s, right? Followed by 3p, right? Then followed by 4s, then followed by 3d, then followed by 4p, then followed by 5s, and so on and so forth. Now, this is actually the order of arrangement of these orbitals, from the lowest orbital to the less stable orbitals. So with this, it's quite important for us to know the maximum number of electrons in each of the orbitals. This is just a quite simple review. S orbital has a maximum number of 2 electrons. The p orbital has a maximum number of 6 electrons. The d orbital has a maximum number of 10 electrons. And the f orbital has a maximum number of 14 electrons. So now, following the order, I think it's going to be quite easy for us to now write the electronic configuration of any of these elements. For example, let's begin with scandium. Scandium Sc with atomic number of 21. So that will give us 1s2 following the order. Because the maximum number of electrons in the s orbital is 2. So that will be 1s2, then 2s2, then 2p6. Right? Because the maximum number of electrons in the p orbital is 6. Then after that, we have 3s2, then 3p6. Now the whole of this, when you count the electron in all, that's 18. We continue, that's 4s2. This makes 20. So, and we are going to 21 electrons. So we're filling 20 electrons there. So the next one is going to be 3d. So that will be 3d1. So this implies that the electronic configuration of scandium is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d1. So we can follow the same logic. Also trying to do the electronic configuration, writing the electronic configuration of others also, like titanium. For titanium, you'll be having Ti, titanium. That will give us the same electronic configuration. You'll be having 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d2. That's 22. Titanium has atomic number of 22. So that gives us the electronic configuration of titanium. So we use the same principle to write the electronic configuration of other elements too. Let's say also we want to write the electronic configuration of manganese, for example. So manganese has an atomic number of, try to recall the acronym that I told you, science thesis verdict, coil masters. So masters as manganese, and that's 25. So if you have to write the electronic configuration of manganese, Mn, so that's 25. So that will give us 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d5. So that makes 25 electrons. So you can see how we can write the electronic configuration of these elements. But I'm going to do something important here. I'm going to give you more descriptions of some of these elements here so that we can have a better understanding and then how to analyze them better. So for example, we have the other element, like let's take possibly cobalt, CO. So what's the atomic number of cobalt? Science thesis verdict, coil masters in Congo, that's 27. So that's 27. So we write the electronic configuration. So following the order, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d7. Now this is actually how to write the electronic configuration of all these elements. However, you can also use a core that is taking into consideration the closest noble gas. So the closest noble gas for the first transition series of argon. So for example, when you have scandium, for example, with atomic number of 21, so the closest noble gas is noble gas of argon, and the noble gas of argon has 18 electrons. So, and for the 18 electrons, it's going to end at electronic configuration of 3p6. Okay, so you'll be writing all others and then you stop at 3p6. So any other one can then continue from there. So if I also want to rewrite the electronic configuration of scandium using the core, so it's going to be argon core with a 4s2 and a 3d1. So that's how to do that. So if you want to write the electronic configuration of iron, for example, so let's take a look at iron Fe. So iron is 26. So following the core, so it's going to be argon core, atomic number of 18. So 18 electrons. So you'll be left with about 26 minus 18. That will give you about 8 to fill into the electrons. So then that's going to give us 4s2, then 3d. So this is now 20. 18 plus 2, 20. I have 6 more. So this is how to write the electronic configuration of that. So we can see. So we can also use the core to write the electronic configuration. Now, noting fully well that in the transition metals from 21 down to 30, as you can see here, so we get to realize that all of these transition metals, especially for the first triad, they are all going to have 4s2, 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 with the exceptions of 2 elements, and they are chromium and copper. Chromium and copper. So when you have to write the electronic configuration of chromium and copper, for example, it's going to be a bit different. So chromium, which has an atomic number of 24, normally following the order we have explained using the argon core, it should give us Ar with a 4s and a 3d. So normally it should be 4s2, 3d4. This should be the electronic configuration of chromium, because this argon core is 18, so that will give us a total of 24. But chromium has an exception because of the rule of stability. Then the electronic configuration of chromium is going to change. So its chromium becomes 4s1 and this becomes 3d5. So this is how to write the electronic configuration of chromium. And the electronic configuration of copper will be Cu29. So that will be argon core. So it's also going to be 4s1, then the 3d10. So these are the only 2 elements in the first triad that will have 1 electron in their 4s orbital, 1 electron in their 4s orbital. All others will have 2 electrons in their 4s orbital. This should be noted. And the reason why we are having this is simply because of stability. The d orbital has about 5 different suborbitals in it, and so when you have electrons, there will be transmission of electrons from the 4s orbital to the what? To the d orbital, to ensure that the d orbital becomes more stable. So that's why there's always transition of electron from the 4s orbital to the d orbital, so as to ensure stability of the electrons. So chromium and copper will have 4s1, 4s1, while the other part becomes 5 and 10 respectively. So this is quite important and crucial for us to note while writing the electronic configuration of these elements. Now, in addition, it's again very important for us to know how to write the electronic configuration of the ionic form of these transition metals. So when these transition metals lose electrons, how do they behave? So we want to know how to write their electronic configuration and what exactly is the principle or the technique that is used in writing this electronic configuration. Now we are going to take few of them. For example, scandium, when you have Sc with atomic number of 21 with 1 electron loss. So if you are to do this, this signifies or indicates that scandium has lost 1 electron. So to write the electronic configuration, this is going to be argon core Ar 4s2 and a 3d1. Now, because it is losing 1 electron, so it has to lose 1 electron from an entity and then becomes an ion. So the scandium will prefer to lose 1 electron from these parts, and so this becomes 1. So the true electronic configuration of scandium now becomes Sc21. So we're going to have this argon core 4s1 and a 3d1. So this is going to be the electronic configuration of scandium ion, that's Sc plus. So we can also think about, let's see what's going to be the electronic configuration of something like Se2 plus, that is scandium with a charge of 2 plus or 3 plus. Okay, let's do that of 3 plus. So we have in Sc21 with a 3 charge. So this implies that scandium is losing 3 electrons. So normally scandium is going to have an argon core this way with a 4s2 and a 3d1. So, but because scandium is losing 3 electrons, definitely it will lose one of the electrons from this and another electron from this. So it's going to lose 3 electrons all through. So the electronic configuration of scandium with a charge of 3 plus becomes Ar 4s0 and 3d0. So this is how to write the electronic configuration of scandium with a charge of 3 plus. So let's look at another one, manganese with a charge of 2 plus, for example. So manganese, what is the atomic number of manganese? So science teaches verdict, coil masters, so that's 25. So manganese is 25. So that will give us, normally 25 is supposed to be Ar 4s2 and a 3d5. But now that scandium is losing 2 electrons, so it will prefer to lose the 2 electrons from this part. So the major one, the electronic configuration of scandium, of manganese with this ion, that's Mn2 plus, that will be argon core, right, with a 4s0 and a 3d5. So that's the electronic configuration of scandium, of manganese 2 plus, that's manganese ion, Mn2 plus. So we can continue to use this logic to write the electronic configuration of other metals too, of other transition metals. So let me pick like 3 more and then we end up on that very part. Okay, for example, if you are to write the electronic configuration of, let's assume, so if you are to write the electronic configuration of the following elements, of the following ions, like Fe2 plus, Fe3 plus, Mn4 plus, Cr3 plus, Cu2 plus, and maybe Zn2 plus, something like this. So let's begin. So as for Fe2 plus, so Fe2 plus will maintain atomic number of 26, so that will be argon core. Normally Fe2 plus, the atomic number of 26 should be 4s2 and a 3d6. Now, but because it is losing 2 electrons, so it's going to lose the 2 electrons from this part, so that will make it to be argon core 4s0 and a 3d6. So that will be the electronic configuration of Fe2 plus. So Fe3 plus, that will be 26 here, so that will be argon core Ar with a 4s2 and a 3d6. So it is losing 3 electrons. Definitely it will lose 2 electrons from here and to lose 1 electron from this. So in the end, this is going to be argon core Ar 4s0 and a 3d5. So that will be for that. Then as for Mn2 plus, Mn4 plus, so manganese, that's atomic number of 25. So that should give us argon core Ar with a 4s2 and a 3d5 normally. Now it is losing 4 electrons. It will lose 2 from here and 2 from here. So that becomes argon core Ar 4s0 and a 3d3. So that will be the electronic configuration for that. So we can pick others too. We have Cr. Let me see if I can put that here. Cr3 plus. That will give me atomic number. What's chromium? We said chromium is 24. Don't forget, chromium and copper will have 4s1 in their d orbital. So that will be argon core Ar 4s1 and a 3d5. So it is going to lose 3 electrons. So it will lose 1 from here and it will lose 2 from here. So that becomes argon core with a 4s0 and a 3d3. So that will be the electronic configuration of Cr3 plus. So we can do the same thing for others, and the same technique is applied for us to solve questions on the electronic configuration of the ionic form of these transition metals. Now, a need for us to be able to identify if a transition metal is going to be paramagnetic or diamagnetic. That's quite important also in questions. So first, a quick reminder on what is meant to be paramagnetism. So paramagnetic. So when do we know that an element is paramagnetic? So a transition element will be paramagnetic when it possesses more unpaired electrons. When it possesses more unpaired electrons in its valence orbital. So when there are more unpaired electrons in its valence orbital, such an element, such a transition metal is said to be paramagnetic. So, for example, how do we identify paramagnetism? We have an orbital this way. Let's assume this is a d block orbital that has divided into 5 different suborbitals. D orbitals are divided into 5 suborbitals. So, okay, so it has a maximum number of 10 electrons, but divided into 5 suborbitals. So when you have to fill in electrons in these d orbitals, according to Hounslow, you have to fill singly before pairing. So this is 1, 1, 1, 1, and 1. So you have to fill once before you start what? Pairing this way, this way, this way, this way, this way. So for example, if you have an element, whose last orbital is about d6, for example, so we divide this into 5 groups. This is 5 suborbitals. So to fill in the electrons, you want to fill in 6, so you fill singly 1, 2, 3, 4, 5, and then 6. So as for this, if this happens to be the valence orbital, then it implies that you have 4 unpaired electrons. Okay, you have 4 unpaired electrons, and then you have 1 paired electron. So this entity, right, an element with this kind of entity is said to be paramagnetic. Okay, this is one of the ways we identify paramagnetic substances or elements. Now, as for diamagnetic substances, so these are identified from also their valence orbital. So diamagnetic, right, diamagnetism. So diamagnetic substances or elements, how do you identify them? They have more paired electrons in their valence orbitals. So when you get to realize that you have more paired electrons in their orbitals, then we say such an element is considered to be diamagnetic. So just like I said, if you have something like this, a d block element, 1, 2, 3, 4, 5, right? So, and then you have d8, for example. So that'll be 1, 2, 3, 4. Let me make it 5. So then we have 8 paired, 6, 7, 8. So you can see here you have 3 paired electrons, 3 paired, and then you have 2 unpaired. So what this implies is that you have more paired than you have paired. So an entity with this type of configuration is said to be diamagnetic. So let's look at a few examples and consider which one is paramagnetic and which is going to be diamagnetic. Now let's take a look at some of these elements like Fe, right, Cu, what else, Mn, and maybe Co. Let's take a look at this and let's see if they are going to be paramagnetic or diamagnetic. Fe, for example, 26. So this is going to be argon core Ar, 4s2, 3d6. So this is the valence orbital, so we divide this into 5 parts. So we need to fill singly before pairing. 6, 1, 2, 3, 4, 5, 6. So we have 3 unpaired electrons. So this implies that Fe is paramagnetic because we have more unpaired electrons than we have paired electrons. So Fe is paramagnetic. So let's look at Cu, that's 29. So that's going to have an argon core Ar. Do not forget that copper and chromium you have 4s1. So this is 18, 19, then this is going to be 10. Right? So for this is having 1, 2, 3, 4. So 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can see this is completely filled, so we say this copper is going to be diamagnetic. So it is having more paired electrons, more paired. So as a result, we can even say that copper is strongly diamagnetic. It is strongly diamagnetic. Okay, so that's it. So let's look at also Mn. Let's look at Mn. Now, Mn, manganese, atomic number of 20, science teaches verdict, coil mass stats, that's 25. So that will give us argon core, 4s2, 3d5. So this is going to be like this. So fill singly, 1, 2, 3, 4, 5. Right, so this is also paramagnetic. In fact, this is strongly paramagnetic. Okay, you can see that. So lastly, we have cobalt. Let's look at that also. Cobalt is having CO. Science teaches verdict, coil masters in Congo, right? That's 20 what? 27. So that's argon core, 4s2, 3d7. So this is going to be like this, right? 1, 2, 3, 4, 5, then 6, 7. So you have 3 unpaired electrons. So this is also going to be paramagnetic. So this is actually how to detect if a given entity will be paramagnetic or diamagnetic. So lastly for today, we want to look at the physical properties of transition elements. So the major physical properties of transition elements are, they are typical metals with high melting and boiling points. So metals generally have high melting and boiling points, with the exception of very few metals. So transition metals generally used to have high melting and boiling points. So it takes a lot of temperature for you to be able to melt them from their solid form into their liquid state. So they are hard solids which are tough, ductile, and malleable. So they are ductile. Ductile simply means they can be drawn into wire. Malleable simply means they can be beaten into sheets. Then they are good conductors of heat and electricity. So that's why they sometimes are used for our home appliances, right? Also in our electrical appliances. Right? So they have high densities with metallic lustrage. So they have a shining property. So they have small atomic volumes. They have magnetic properties. So we have talked about these magnetic properties. So they can be paramagnetic and they could be diamagnetic. So paramagnetism simply means that they have the ability to get attracted to a magnetic field. And diamagnetism simply refers to as their inability to be able to be attracted. So meaning they will be repelled by what? By magnetic field. So this is going to be what we are going to do for today. In our subsequent series, we shall be discussing the chemical properties of transition metal. Have a nice day. Bye for now.